So in this last portion of Chapter 4, we're going to talk about those constitutional isomers. Remember, constitutional isomers are our structural isomers, where they have the same formula, but they have different connectivities. So we're actually going to rearrange all of our atoms in different connecting orders. So to just give you an example, here's an example for C11H24, where we have 11 carbon atoms and 24 hydrogens. And there are going to be a ton of ways that we can actually draw this structure that would be considered our structural isomers. So both of these have the formula of C11H24, but you'll notice that we've connected them very differently. We would name both of these structures very, very differently. This one over here is a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain as our parent, so it would be named as an octane. The one over here on the right, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be named as a nonane. There's a lot of different ways that we can put together structural isomers. And the key is that they have different connectivities, but they have the same number of atoms. Another one that we can look at is with the structure of C6H12. One of the ways that we can draw C6H12 has been one of our focuses for this chapter, and that's that nice cyclohexane ring. But we can also take this and we can have a straight chain as well with a double bond in it. This will also have the formula of C6H12. So with our structural isomers, there's lots of different ways that we can draw them. And structural isomers will oftentimes have different properties associated with them because we have connected the atoms in a different way. One of the things that we're going to use to help us understand structural isomers and different ways that we can draw structural isomers based on our formulas is going to be the use of the index of hydrogen deficiency, which we will abbreviate IHD. What this does for us is it determines the degree of unsaturation within our molecule. So what we mean by saturated is the maximum number of hydrogen atoms that a molecule can contain. So a saturated molecule in organic chemistry is a molecule that has all the hydrogens on it possibly could have, which means all of our atoms are sp3 hybridized. So when we talk about degrees of unsaturation, we're talking about taking some of those hydrogen atoms away. And in order to do that, we have to have some form of pi bonding within our structure, or we need to have some form of a ring where we have lost hydrogens because we're connecting our atoms together. So our degree hydrogen index will give us some information on the types of structural features that our molecule will have based on this calculation. So the way that we are going to calculate our IHD is it is equal to 2 times the number of carbon atoms that we have in our structure plus 2 plus the number of nitrogen atoms that we have in our structure. From that, we're going to subtract the number of halogens, so we'll typically denote halogens with an X, and we're going to subtract the number of hydrogen atoms that we have in our structure as well. And then we're going to divide that number through by 2. And this will give us that degree of unsaturation. So C represents, again, the number of carbon atoms, N is the number of nitrogens, X is the number of halogens, H is the number of hydrogen atoms. So 2 times the number of carbon plus 2 plus nitrogen atoms minus the number of halogens minus the number of hydrogens, all divided through by 2. This number that we're going to be looking at is going to be equal to either 1 ring in our structure or 1 pi bond. So if I do my calculation and I get a value of 0, it means I have a saturated structure. There are no pi bonds and there's no rings within our structure. If I do my calculation and I get a value of 1, it tells me that I have either a ring within my structure or I have 1 pi bond, which would mean 1 double bond within my structure. If I have a value of 3 for my IHD, it would tell me that I would either have 3 rings within my structure, or I would have 3 pi bonds within my structure, or any combination therein. 1 ring, 2 pi bonds, 2 rings, 1 pi bond, but I would have to account for that 3 and some combination of rings and pi bonds. The IHD for isomers must be the same. So remember, isomers have the same formula, So all of my isomers must have the same IHD, not necessarily the same structures. So you think back to cyclohexane and the cyclohexene and this hexene structure that we just drew for C6H12. One had a ring structure, one had a pi bond, but both of those would have an IHD equal to 1. So let's look at a couple of examples here. So take a moment, pause the video, and see if you can calculate the IHD for each one of these examples. I've given you 2 formulas and 2 structures. See if you can calculate those IHDs for me. So for our first one, where we have our formula of C6H10, my IHD is going to be equal to 2 times the number of carbon atoms, which is 6, plus 2. There are no nitrogen atoms, there are no halogens, so from this I'm going to subtract the number of hydrogen atoms and then divide through by 2. So this would have an IHD of 1. So again, the way that I could draw this is I could draw it with a ring, or I could draw it with 1 pi bond, which would be a double bond for us. For the next one, the C5H7Cl, 2 times the number of carbon atoms, which is 5, plus 2. There are no nitrogens, but there are halogens, so I'm going to take 1 halogen away and then subtract my number of hydrogens, which is equal to 7. So all of that then divided by 2 will give me a value of 2. So it means that this structure has 2 rings, or it would have 2 pi bonds, or it would contain 1 ring and 1 pi bond. The idea of this structure having 2 rings is probably not valid because we only have 5 carbon atoms. And we've talked about the sizes of rings we need to have in order for rings to be stable. So it's very unlikely that we have 2 rings. So we probably have isomers that have 1 ring and 1 pi bond, or a structure that has 2 pi bonds, which could either be 1 triple bond or 2 double bonds. For the next structure that we have drawn here, we really would not need to use the formula. The IHD for this structure should be equal to 0. There are no pi bonds and there are no rings in this structure, so the IHD would be equal to 0. We can do the same thing for the structure that is given below. The IHD here should be equal to 1. We have 1 ring, so we have 1 degree of unsaturation. I do want to point out one more thing before we end our slideshow, and that is if I have an IHD equal to 4 or higher. Anytime we have an IHD equal to 4 or higher, it is likely that we have a benzene ring, especially if the number of carbon atoms that we have is equal to 6 or around that value of 6. It can't be less than 6, but if we have a small number of carbon atoms. Because an IHD of 4 implies that we have 4 degrees of unsaturation, which is a lot of unsaturation for very small molecules. But if we look at a benzene ring, which is only 6 carbon atoms, and it has those alternating single and double bonds, one benzene ring accounts for 4 degrees of unsaturation. It has 3 pi bonds, and it has 1 ring. So one benzene ring itself has a degree of unsaturation of 4. So if you have these very large IHD values for relatively small numbers of carbon atoms, it is very likely that you have some form of a benzene ring as part of your structure. So we can use these IHDs to really help us understand what are some structural features that we can have, and also help us to dictate what are some differences that we can have within our isomers.